Namaskar, hello, and a very warm welcome to CIET NCERT's live phone-in interactive program. Well, this is our webinar series, Listening to Learn, and this is our 47th episode for this particular session. My name is Tanvi Khurana, and here today we are going to discuss another topic for science which is very important, and I'm sure you must have all heard about the James Webb Space Telescope. Yes, that's what our topic is all about, James Webb Space Telescope, out where the stars do not twinkle. जिसे हम हिंदी में कहेंगे जेम्स वेब स्पेस टेलीस्कोप, वो जहां तारे नहीं टिमटिमाते। क्यों है आज का हमारा इस साइंस का कार्यक्रम इतना खास, आपको पता चलेगा इस कार्यक्रम में। अगर आप हिस्सा लेना चाहते हैं तो ज़रूर हमारे साथ जुड़िए, आप हमें फ़ोन कर सकते हैं। हमारा नंबर है 8800440559। इस वक्त आप हमें लाइव देख रहे हैं ई विद्या चैनल नंबर 9, चैनल नंबर 10, 11 और 12 पर। इसके सर्टेन ईमेल आईडीज़ हैं जिन पर आप कांटेक्ट कर सकते हैं, जिस पर आप अपने सवाल लिखकर हम तक पहुंचा सकते हैं। और साथ ही साथ इस वक्त आप हमें लाइव देख रहे हैं हमारे यूट्यूब चैनल पर भी, जो कि है NCERT ऑफिशियल। उसके लाइव चैट बॉक्स में भी आप अपने सवाल लिखकर हम तक पहुंचा सकते हैं। आज का जो हमारा कार्यक्रम है वो हर 2 हफ्ते में एक बार आता है, once in 2 Fridays, well, if I should say. And हम हर बार एक साइंस का एक खास कार्यक्रम लेकर आते हैं, एक नया टॉपिक डिस्कस करते हैं, चाहे वो हमने पास्ट में डिस्कस किया हो बैटरी मैन्युफैक्चरिंग और बहुत सारी मेडिसिन की डिस्कशंस, एंड देन सॉइल वाटर क्वालिटी मैनेजमेंट एंड विंड टनल एंड व्हाट नॉट। अगर आपने हमारे पुराने कार्यक्रम नहीं देखे हैं तो भी आप उन्हें देख सकते हैं NCERT ऑफिशियल हमारे यूट्यूब चैनल पर, वो सभी मौजूद है। एक प्रोग्राम है जो कि आउटरीच प्रोग्राम है। नो मैटर वेयर यू आर सिटिंग, व्हाट इज द टाइम जोन एट योर एंड, यू कैन वॉच इट एनीवेयर एनी टाइम. And this is not at all an ordinary series. We have a very special guest with us. But for the introduction of that special guest, we have our coordinator of this program, the brain of this entire program, and he is nobody else but Dr. Gagan Gupta. Sir, a very warm welcome.
नमस्कार तन्वी, नमस्कार दोस्तों, एक बार फिर से सादर प्रणाम, नमस्कार। आप सबका स्वागत है इस वेबिनार सीरीज़ में, जो कि आज से लगभग 2 बरस पहले शुरू हुई थी। आज इसका 47वां सेशन है। और आपको जस्ट एक क्विक रिव्यू के लिए कि ये प्रोग्राम काउंसिल ऑफ साइंटिफिक एंड इंडस्ट्रियल रिसर्च दिल्ली, गवर्नमेंट ऑफ इंडिया के कोलैबोरेशन में शुरू हुआ था। और आज का जो प्रोग्राम है, आज का जो सीरीज़ है, ये 47 सेशन है, जिसमें कि मेरी साथी तन्वी ने अभी बताया कि आज हम जेम्स वेब स्पेस टेलीस्कोप के बारे में बात करेंगे। देखिए, धरती पर हमको तारे टिमटिमाते हुए नज़र आते हैं अर्थ पर। इसकी वजह है एटमॉस्फेरिक रिफ्रैक्शन, हमारा एटमॉस्फेयर। लेकिन अगर किसी तरह से हम इस एटमॉस्फेयर के बाहर किसी स्पेस स्टेशन पर पहुँचें तो वहाँ पर कोई एटमॉस्फेयर ना होने की वजह से ये रिफ्रैक्शन फिनोमेना नहीं मिलेगा, तो तारों का टिमटिमाना वहाँ से नहीं दिखेगा। आज इसी चर्चा पर हम बात करेंगे। दोस्तों, आज का ये प्रोग्राम हमारे पूर्व में हुए 2 प्रोग्रामों की श्रेणी में ही है। आप याद दिलाऊं, 16 नवंबर 2021 को हमारे साथ प्रोफेसर अनिल भारद्वाज, जो कि डायरेक्टर हैं फिजिकल रिसर्च लेबोरेटरी, भौतिक शोध अनुसंधान शाला अहमदाबाद से, उन्होंने हमें बताया था इंडियन प्लेनेटरी मिशंस या भारतीय ग्रही मिशनों के ऊपर। और उसमें उन्होंने सन के चारों तरफ चक्कर लगाने वाला इंडिया का, हमारे भारत का एक प्रोग्राम के बारे में बताया था, जिसको कि शुरू होना है और जिसको कि एक L1 ऑर्बिट पर जाना है। उस L1 ऑर्बिट में क्या था, ये सब बातें उसमें आप देख सकते हैं दोबारा से, जो कि हमारे NCERT ऑफिशियल यूट्यूब चैनल पर भी है, और साथ साथ हमारी वेबसाइट ncert.nic.in/webinarseries.php, इस पर आप देख रहे हैं। इस इवेंट सेक्शन में आपको सारे सत्र मिल जाएंगे। और उसी के साथ साथ एक मार्च में हमारा 11 मार्च को एक सेशन हुआ था, जिसमें कि हमारे साथ स्पेस एप्लीकेशन सेंटर अहमदाबाद से दीपक मिश्रा जुड़े थे, और उन्होंने इंडियन स्पेस प्रोग्राम्स के बारे में बात की थी। आज का जो प्रोग्राम है, आज का जो सत्र है, जैसे कि तन्वी जी ने हमें बताया टेलीस्कोप के बारे में, जिस टेलीस्कोप के बारे में से हमें दूसरे इस ब्रह्मांड में दूसरी आकाश गंगाओं और दूसरे ग्रहों के बारे में हमें मालूम पड़ेगा। हमें उम्मीद की जाती है कि हमें इसके खोज के बारे में हमें नई नई चीज़ें मालूम पड़ेंगी। इस टेलीस्कोप से। आज उसी टेलीस्कोप के बारे में मेरे साथी, मेरे दोस्त डॉक्टर आनंद नारायणन, जो कि इंडियन इंस्टीट्यूट ऑफ स्पेस साइंस एंड टेक्नोलॉजी IIST तिरुवनंतपुरम से आज हमारे साथ जुड़े हुए हैं, और अभी थोड़ी देर में मैं आपका उनके साथ बात कराऊंगा। और आज आप देखेंगे कि देखिए बहुत ही एक्साइटिंग टॉक है, और आज आप देखेंगे जो कि पिलर्स ऑफ क्रिएशन तक जाएगा, और पिलर्स ऑफ क्रिएशन तक की जो इमेजेस ली गई हैं, चाहे वो हबल टेलीस्कोप था, चाहे वो ESA टेलीस्कोप था, चाहे वो जेम्स वेब टेलीस्कोप है जो कि अक्टूबर में ली गई, इन सब के बारे में चर्चा करेंगे। इससे पहले कि डॉक्टर आनंद अपनी बात शुरू करें, मैं उनका तारुफ जरा तेजी से आपके साथ कराना चाहता हूँ। My friend Dr. Anand Narayanan is a professor at the Indian Institute of Space Science and Technology, Thiruvananthapuram, which is an institute under the Department of Space, Government of India. Previously, Dr. Anand was a postdoctoral scholar in the Department of Astronomy at the University of Wisconsin, Madison, in the United States. This is the place where our Nobel laureate Hargobind Khurana worked. Dr. Anand earned his PhD in the Masters in Astrophysics from the Pennsylvania State University in the United States. Anand holds a BTech in Electrical and Electronics Engineering from the College of Engineering, Thiruvananthapuram. His research involves understanding how galaxies and other large-scale structures form in our universe. Anand also has a keen interest in astronomy education and public outreach programs. He has scripted, directed, and anchored a series of 7 episodes on astrophysics in Malayalam for the government of Kerala's television channel Victors. The series won the Kerala State Government's Award for the Best Educational Program on Television for the year 2014. More recently, Anand Narayanan scripted and directed a half-hour documentary in the English on the history of 180-year-old Travancore Observatory. The film won 2 awards on the 10th National Science Film Festival of India. Dr. Anand has also done programs for All India Radio on topics in astrophysics. Friends, Dr. Anand is with us. Welcome Dr. Anand. आज आपके साथ बात करेंगे और बहुत मजा आएगा, मुझे पूरा भरोसा है. And at the same time we thank Indian Institute of Space Science and Technology, Department of Space, for collaborating with NCERT for this session. We also thank the NASA and the ESA, the European Space Agency's websites, from where some of the slides have been taken. We acknowledge the permissions or the contributions from the NASA and ESA websites. It's all yours now, Dr. Anand. Welcome once again.
Thank you. Thank you, Dr. Gagan Gupta. Thank you, Tanvi ji, for the very generous introduction. Namaskaram and Happy New Year to all the teachers, students, parents, and everybody who is tuning into this program. I want to thank wholeheartedly the entire staff of NCERT for giving me this opportunity to be part of this very popular Listening to Learn program. I am going to be talking about a topic that is in the public domain for the last 1 year, which is about the James Webb Space Telescope. New era in astronomy began on December 25th of 2021 with the successful launch of the James Webb Space Telescope. JWST, as many of you already know, is the largest deployable space telescope ever built by humankind. It is an engineering marvel in all sense of the word. And so from 2021, more than a year has gone by since the launch of JWST. The field of astronomy and astrophysics is looking at a very exciting future where many important discoveries are going to be made, a lot of which is going to be made by the James Webb Space Telescope. So in today's presentation, which will be for about 45 minutes or so, what I'm going to be doing is I'll be giving an overview of JWST. It's a very unique, fascinating design, its capabilities as a telescope, as a scientific instrument, to study a wide range of objects that are both near and far to us, from objects within the solar system to the most distant parts of the universe. So many of you will be knowing this. JWST was launched in December of 2021 using an Ariane 5 rocket. Ariane 5 is a European launch vehicle. Ariane 5 was chosen after a lot of careful consideration by the partnering space agencies, which is the European Space Agency, the American Space Agency, which is NASA, and the Canadian Space Agency. So they debated for a long time on what launch vehicle to choose, and Ariane 5 was finally chosen for some of its unique features. What you are seeing here is a schematic diagram of the Ariane 5 rocket. It's about 50 meters high, and when it is fully loaded, Ariane 5 weighs about 800 ton in mass. Okay, so a ton is 1,000 kilogram. The rocket is capable of putting 6,000 kilograms of payload cargo into what is known as an L2 transfer orbit. So I'll be talking about L2 a little bit later on. Ariane had a lot of successful launches, almost 80 consecutive successful launches. So it has a very clean track record, which is one of the main reasons why it was chosen. The cargo bay of Ariane, which is at the top of this launch vehicle, it's not very big. So for a telescope of the size of the JWST, which is as big as a tennis court, if you know what it is. So for a telescope of that size to fit into such a small portion or the cargo bay of Ariane, the telescope had to be folded in. So this, what you are seeing here, is a blow up of the top part of the Ariane 5 rocket, and you can see the JWST telescope folded into it. And this is how it fits into the rocket. And once the rocket lifts off at a certain stage, the upper stage opens up and the telescope gets separated from the rocket. So the purpose of Ariane 5 is to basically put JWST into orbit. Now, what you're going to see now is a real-time video that shows the separation of the James Webb Space Telescope from the Ariane 5 launch vehicle's upper stage. So you can see here the JWST is being ejected out from the upper stage of Ariane 5, and you can also see the Earth below. And subsequent to this, the solar panels of JWST are deployed, they open up. This whole this separation of JWST from the launch vehicle, it happens about 20 minutes after liftoff, after the launch. And once JWST is separated, about 1 minute later, the solar panels of the solar arrays, which power the entire observatory, they slowly open up. So this folded JWST telescope, this entire observatory is unfolded in a carefully choreographed series of steps before beginning to make observations. And that process takes about 6 to 9 months. So though JWST was launched in December of 2021, the first observations with the telescope happened only in June of 2022. So that's the time it takes for JWST to reach a particular point in its orbit, and also for all the components of JWST to start functioning. So you can see the solar panels now slowly expanding out in the video. Now, so where is JWST positioned? Where in outer space is the Webb telescope positioned? Now, what you are seeing here is a picture of the sun and the earth, and you can also see the moon that is going around the earth. Now, any object that has mass, as you would have studied in school, is capable of exerting gravitational force on other objects. So gravity is an attractive force. The earth is going around the sun. What keeps the earth in its orbit is a balance between two forces. One is the gravitational pull from the sun, and the other is a force called the centrifugal force that pushes Earth tangentially outwards in its orbit. So there's a perfect balance between the centrifugal force and the gravitational pull from the sun, which is what keeps the Earth in its orbit. Now, if you consider the Sun-Earth system, there are points in the orbital plane of the Earth around the sun where the net gravitational attraction from the sun and the Earth can be balanced by the centrifugal force of orbital motion. So there are 5 such points. These are called Lagrange points, L1, L2, L3, L4 and L5, as you can see marked in this figure. Now, if you put a smaller object like a satellite or an observatory like JWST at any of these 5 points, L1, L2, L3, L4 or L5, it will remain in that position relative to the sun and the earth. So that is what is unique about these Lagrange points. The points are called Lagrange points because mathematically these points were first derived by a French mathematician called Lagrange. So it's named in his honor. Now what is of interest to us is the point L2, which you can see in this figure, which is behind the earth. Now L2 is located about 1.5 million kilometers directly behind the earth as viewed from the sun. Now 1.5 million kilometers might seem like a very large distance, but remember that it is only 1% more than how far away earth is from the sun. So in this figure it is exaggerated a little bit. L2 is only 1% more than how far away earth is from the sun. A spacecraft that is placed at this point at L2 will be more distant from the sun compared to earth. And JWST is positioned at this L2 point or in an orbit around the L2. Now JWST is not the first satellite or the first observatory to be positioned in L2. There have been other satellites like WMAP, Herschel, Planck, Gaia, which are all at the Sun-Earth L2 point. And that's where JWST also is. Now, since there are multiple telescopes at L2, now you may be wondering whether there is a chance for these telescopes to collide with each other. That is not going to happen. JWST will not collide with any of them because none of them, including JWST, is exactly at L2. They are all orbiting around L2 and they are really far apart. So what you are going to see in this animation here is the orbit of JWST around the L2 Lagrange point. So it's called an L2 halo orbit. JWST goes about 350,000 kilometers up and down, and this going up and down avoids the telescope being in Earth's shadow. So it will take about 6 months to go once around the halo orbit. So that means that it will complete 2 orbits around L2 by the time it goes once around the sun, JWST. Now, the next question is why go to space? Dr. Gagan Gupta already mentioned one of the advantages of putting an observatory in space. In terms of cost, it is definitely much more expensive to put a telescope in space compared to building an observatory on ground. But there are some definite advantages of putting a telescope in space above the Earth's atmosphere. Now, as you know, Earth is surrounded by this blanket atmosphere, and the atmosphere is never still. It is always turbulent. Okay? The gases in the atmosphere are constantly moving. Now, if you think about light that is coming to Earth from the distant parts of the universe, from stars, star clusters, planets, galaxies, etc., they travel through the universe for the most part without any hindrance. But finally, when they cross the 100 kilometers of the Earth's atmosphere, because of the turbulence in the Earth's atmosphere, the light is severely affected in multiple ways. Okay? So ground-based telescopes have to deal with this problem that the turbulence in the Earth's atmosphere degrades the quality of the image. So to illustrate this point, let me show you a real image. So what you are looking at here on this image are a number of stars as seen by a telescope on ground, on the surface of the Earth. Okay. Now that same patch of the sky, if we observe from space, then this is what we will see. You can see that once you are above the Earth's atmosphere, you get a clear view of the universe. And this is very, very important if you want to study the universe with a lot of clarity. Okay, so the turbulence in Earth's atmosphere degrades the quality of images. So one way to overcome this problem is to put a telescope that is above the Earth's atmosphere. The second reason of having an observatory in space is that, again, atmosphere is the key component here. Earth's atmosphere is opaque to most of the electromagnetic spectrum. So what you are seeing here is the entire range of the electromagnetic spectrum. In school, you would have studied gamma rays, X-rays, ultraviolet rays, visible light, infrared rays, microwaves, radio, etc., which forms the entire electromagnetic spectrum. Now, from the surface of the Earth, it is not possible to access this entire electromagnetic spectrum. That is because the Earth's atmosphere either reflects or absorbs a lot of light. Electromagnetic radiation is nothing but light. So except for the visible light, which is what we all see with our unaided eye, and some amount of radio light, radio electromagnetic waves, the atmosphere cuts off light of all other energies coming to us from outer space. So the opaqueness of the atmosphere at all other wavelengths is one of the other main reasons why it is important to put an observatory in space. Suppose you want to study the universe at X-rays or ultraviolet or infrared, you have to go to space. Space is a much better observing platform compared to Earth. So that is, those are some of the key reasons why space observatories are so crucial in astronomy. Now, as I mentioned, JWST is at a distance of 1.5 million kilometers away from us. That's like a really far away distance. There are actually places that are outside the Earth's atmosphere which are much more closer to the Earth. For example, most of the satellites that our Indian Space Research Organization launches, ISRO launches, they are all in more or less in LEO orbit, what is known as the low Earth orbit, which is somewhere between 200 kilometers above sea level to 2000 kilometers above sea level. The Hubble Space Telescope, you must have heard of it, the Hubble Space Telescope, which was a predecessor to JWST, is also in the low Earth orbit. The International Space Station, where astronauts are routinely living, that is also in low Earth orbit. So if low Earth orbit is available and if it is much more closer to Earth, then why put JWST in the L2 Lagrange point, which is 1.5 million kilometers away, when you can put something that is a few hundred kilometers away from Earth? Obviously, there are some advantages in putting JWST in L2. The reason is that JWST is optimized to observe the universe at infrared light. The instruments for doing this, the cameras, the spectrographs, etc., they have to be at very cold temperatures, temperatures less than minus 200 degrees centigrade, if they have to function effectively. In low Earth orbit, if JWST is in low Earth orbit, then the heat from the Earth and the Sun will affect the performance of the back-end instruments on JWST. They will contribute what is called instrumental noise, which means data quality will be affected. Performance of the instruments will be affected. Now, one way to overcome this is to cool the telescopes and instruments to sub-zero temperatures. But to cool them, if you are putting the telescope in low Earth orbit, then you need a lot of cooling technology, cryogenic cooling technology. Just like your refrigerators have coolants in it, and if you use the refrigerator for a very long period of time, fridge for a very long period of time, you will find that the coolant is going down, and therefore the cooling effect of the fridge is also going down. So occasionally you have to refill this coolant. So additional cryogenic technology is needed. The amount of cooling agent or refrigerant that can be carried to space is limited. And this in turn limits the lifespan of the mission. So now which is why low Earth orbit is not a preferred position for an observatory that is fine-tuned to study the universe at infrared wavelengths. Now, once you go to L2 Lagrange point, which is where JWST is, if you shield the spacecraft or the observatory from direct sunlight, then immediately you achieve the temperature of empty space, which is very, very low, just a few degrees above absolute zero. So this is called passive cooling. And so the advantages of putting L2 is JWST is going to observe the universe at infrared, which requires low operational temperatures. And also from L2, JWST has an uninterrupted view of the universe. It's never in the Earth's shadow. And though far away from Earth, an observatory in L2 will be relatively stable, requiring only small orbital corrections from time to time. So there are some definite advantages in putting an observatory in space. So now if JWST is at a distance of 1.5 million kilometers, how do we control it? How do we send commands to it? How do we tell the JWST telescope where to look in the universe? Now all this is done as part of ground operations from a place called the Space Telescope Science Institute. This is an institute which is located in the state of Maryland in North America, that is US. STSCI, as it is shortly called, has been the ground operation station of the Hubble Space Telescope ever since it was launched in 1990. All the command and control of the Hubble Space Telescope was done by Space Telescope Science Institute. The same institute is going to be the place which will command and control JWST, taking care of its science operations and all data processing. So how does communication happen between STSCI and JWST? How does STSCI, Space Telescope Science Institute, communicate with JWST? All commands and data are routed through what is known as the Deep Space Network, DSN for short. DSN or Deep Space Network is an international array of giant radio antennas located at different parts of the world. These are called ground stations. Now, the Deep Space Network would support the command and control of JWST, just like it is supporting the command and control of many space missions. So, data is sent from STSCI to the Deep Space Network. From the Deep Space Network, command is sent as electromagnetic waves to JWST. From JWST, the data that whatever telescope is observing, the data comes to the Deep Space Network. From there, it is routed to the Space Telescope Science Institute. Now let's move into the design of the James Webb Space Telescope. JWST has a very sophisticated design. I'll just briefly mention some of the highlights of the telescope itself here. Now there are three main flight systems for JWST. Okay. One is the optical telescope element system, which is another set of words for the telescope itself. So optical telescope element or OTE system is the mirror of the telescope and all the supporting and stabilizing structures. The second important flight system is the spacecraft element. Now the spacecraft element, which includes the spacecraft bus and the sun shield, this provides the necessary support functions for the operation of the Webb observatory. For example, electrical power subsystem. Okay, so you need electrical power to run the observatories, to run the detectors, to run the onboard computers. So for that you need electricity. That electricity comes from solar panels, but the solar panel, whatever energy the solar panels are absorbing, it has to be routed to the devices. That is given by the electrical power system. Then there is the communication subsystem. How do you control the flow of data in and out of the JWST? That is done by the communication subsystem. Then there are other subsystems like propulsion subsystems, which tells JWST where to point, how to stay in orbit, etc. So all these are the second main flight systems of JWST. And lastly, and most importantly, is the back-end instruments of the telescope. So the telescope's purpose is to only collect light. If you want to record that light, if you want to analyze that light, and if you want to make it scientifically meaningful, you need back-end instruments. So back-end instruments would mean cameras, spectrographs, etc. I'll be talking about it later on. So all that is part of what is known as the ISIM, which is the Integrated Science Instrument Module. So these three together form the total flight systems of the James Webb Space Telescope. Let me show you a picture which will give you a better idea of all of this. So this is how JWST looks like when it is fully opened up. This is how it is right now at L2. This is a drawing, of course, and you can see the optical telescope element, which is the mirrors of the telescope itself, and then you can also see the ISIM, which is behind the mirrors. That's where all the instruments are. Okay. So now let's discuss a few things about the main mirror of the telescope. This photograph shows the hexagonal mirrors of JWST and their honeycomb-like configuration or arrangement. This is the main mirror of JWST, and its purpose is to collect light from distant objects. JWST, whatever JWST is looking at, if the JWST is looking at planets, then it will collect light from those planets. If it's looking at stars or star clusters, then it will collect light from that. Now, you can see that the entire mirror is made of smaller hexagonal segments. Now, each of those segments is about 1.3 meter in size, and there are 18 of them. Together, when assembled together, these 18 mirrors, it forms what is called the primary mirror of the James Webb Space Telescope, and it will have a total diameter of roughly 6.5 meters, and it will have a shape that is concave. Concave means it is curved inwards. So the primary mirror is a concave mirror, segmented mirror with a size of about 6.5 meters. Now, in addition to the main honeycomb mirror that you just now saw, JWST has two other mirrors. These are called secondary and tertiary mirrors. The primary mirror is concave. The secondary mirror, which is about 0.7 meters in diameter, is convex. And there is also a tertiary mirror, and the purpose of each of these mirrors is different. Now, what you're going to see in this animation is what happens when light falls on the primary mirror of the James Webb Space Telescope. So JWST is looking at some distant astronomical object. So light comes and falls on the primary mirror, the segmented primary mirror. That light gets focused on the secondary mirror. From the secondary, that light goes through a small hole in the primary, and from there it goes to the ISIM module, which is where all the science instruments are kept. And that is where the light gets recorded and analyzed. So this is the optical layout of the James Webb Space Telescope. Now, often people compare JWST with its predecessor, the Hubble Space Telescope. As you probably know, for the last 30 years or so, Hubble has been providing astronomers with a wealth of data sitting in low Earth orbit. Hubble has completely transformed the way we look at our universe, and JWST is a successor to Hubble. So now if you compare these two telescopes, JWST and Hubble, it's useful to do that comparison just to appreciate and understand how much bigger and how much more potential JWST has as a telescope. Okay, so so here what you are seeing are the primary mirrors of Hubble and JWST. The primary mirror of Hubble Space Telescope is 2.5 meters in diameter. The primary mirror of JWST, which is made of segments of smaller mirrors, 18 segmented mirrors, is 6.5 meters in diameter. So now the question is, why build bigger mirrors? Why is it good to have larger mirrors? And the reason is that the bigger the primary mirror, the more light it can collect. In other words, larger mirrors have higher light collecting power. Now, more light collecting power means the telescope will be able to see fainter and farther into the universe. So JWST has a collecting area that is 7 times bigger than the Hubble Space Telescope, which means that it can see objects that are much more fainter than what Hubble could see in the universe, and therefore it can also see much farther into the universe than any previous telescope could. So can see fainter with more light collecting area. The other advantage is the bigger the size of the primary mirror, the better will be what is called spatial resolution. Spatial resolution is nothing but the ability of a telescope to distinguish two closely separated objects in the sky. So if you have two stars that are sitting very close to each other in the sky, whether your telescope will be able to see them as two separate stars or see them as one star, that depends on how big the primary mirror is. The bigger the primary mirror, the more will be the spatial resolution. Now, the mirrors, they are, as I mentioned, they are concave mirrors, and there is a particular design that goes into the construction of these mirrors. It is called an anastigmatic system. That means that the optical elements are arranged in such a way that most of the important optical aberrations, like spherical aberration, coma, maybe you have studied these in school. These are some aberrations that happen when when we try to focus light onto a detector plane. All these aberrations are removed. So these JWST has what is known as an anastigmatic system, and whatever I just mentioned here earlier is already there in the slide. And what is really interesting is that these mirrors are made not of glass but of a material called beryllium. Those of you who have studied chemistry would know that beryllium is one of the chemical elements. So these mirrors are made of beryllium. I'll be talking about it in a minute in a little bit more detail, and it has been given a gold reflective coating. So to make a mirror, we need a material with a smooth surface. That is what you need if you want to make a mirror. On that surface, you have to apply a reflective coating. Only then it will become a mirror. Now, in the mirrors that we use at home, glass is the material that we use as the smooth surface, and on that glass we coat aluminum. Sometimes a single layer, sometimes multiple layers of aluminum. When we coat this glass layer with aluminum, it becomes a mirror because aluminum coating gives it reflectivity. Now, glass is therefore called a mirror blank. Okay. In JWST, the mirror blank is made of beryllium. So what you are looking at here is one of the hexagonal segments of the primary mirror, and which is made of beryllium. Now, the reason why beryllium is chosen is because beryllium is very light. Compared to glass, it's very, very light. It is very strong, and it is good at holding its shape. It is good at retaining its shape across a range of set temperatures, especially at cold temperatures. So remember that JWST is going to operate at sub-zero temperatures. So you want the mirror to be able to withstand those cold temperatures, and beryllium is a good element that has that property. Okay, so what you're seeing here is one of the mirror blanks made of beryllium, and it is about 1.3 meters in size, and each of these blanks weigh about 20 kilograms. Okay. Now, when you apply a gold coating to it, so here you see the mirror blank, which is made of beryllium with gold coating on it. Once you apply gold coating to it, it becomes highly reflective. There are other materials that you can use for coating. For example, you can use silver, aluminum, or copper, but gold has some advantages over all these things. Later on in the question and answer session, if you are interested, I can go over this. So this is the secondary mirror of JWST, which is also coated with gold. And as I mentioned, since JWST is optimized to observe the universe at infrared wavelengths, we need to make sure that the telescope can operate at very cold temperatures. And this is achieved with the help of what is called sun shields. So to achieve thermal insulation, that's what it's called, you want to prevent heat from entering into the telescope system, the optical telescope system. So to achieve this thermal insulation or thermal stability, there is a 5-layer sun shield that acts like an umbrella, that acts like a parasol, providing shade. So this sun shield will always be between the sun, earth, and the telescope. And so on the shadow region of the sun shield, which is where the JWST mirrors and instruments are, the temperatures are going to be very, very low. Typically about 40 Kelvin or so, which is about minus 223 degrees centigrade. So light from the sun and the earth get reflected by this parasol, these sun shields, and that gives the passive cooling for the telescope. Okay. So now what you are seeing here is the sun shield, the 5 layers of sun shield fully stretched out and opened up at ground at the Goddard Space Flight Center where this was put together. The sun shield is about the length of a tennis court, which is about 20 meters by 10 meters across. And it is made of an interesting composite material called Captain, and it's a polyimide material, and it acts like a thermal insulator blanket. So in this video, you can see the 5 layers of sun shield being slowly stretched out. So this is a time-lapse video. The actual process happens very slow, and we are just running it in fast-forward mode. So at the time of launch, the entire sun shield is folded and put into the telescope system itself so that it can fit into the cargo bay of the Ariane 5 launch vehicle. Now let's quickly look at the back-end instruments, the instruments that are at the heart of the James Webb Space Telescope. JWST, as I mentioned, was built with some specific science codes, okay, which I'll talk about in a minute. All of those science codes require one common feature, which is that the telescope and its instrument should be capable of observing the universe at infrared wavelengths. So all the 4 instruments on JWST, the NIRSPEC, NIR, ISS, which is a near-infrared imager and slitless spectrograph. There is a camera that can record infrared light. So all the cameras and spectrographs on JWST, they are all designed to collect infrared light. And there are 4 such instruments, and together they do the science. Okay? So now let's quickly move into the science with JWST. JWST is a general purpose observatory. Now, what that means is that JWST was designed and built not to study one particular object in the universe. You can use JWST to study any object that is emitting infrared photons, infrared light. So it's a general purpose observatory. At the same time, the telescope and its instruments were also designed keeping some primary science objectives in mind. So one of the major goals of JWST is to discover the first luminous structures that formed in our universe, right at the very edge of the observable universe. Okay. And the other primary science goal is to understand how galaxies have evolved over cosmic time, how galaxies have transformed in their shapes and sizes over the past 13 billion year history of the universe. The third primary science goal is to study in depth the birth of stars and planets and their early evolution. And lastly, and one of the most important themes, is to find Earth-like planets around other stars. So these are called habitable worlds, planets that are similar to Earth, where the conditions are conducive for life, favorable for life. And all of these require the ability to take pictures and to record spectra at infrared wavelengths. The science goals are not restricted to these, but these are the main science drivers. So let's look at one or two of these science objectives. One of the cool things in astronomy is that night sky acts like a time machine. Okay? It takes light some finite time to reach us from the distant objects in the universe. That is why in astronomy, we use the concept of light year to talk about distance. When we say a star is 100 light years away, what we mean is that light has taken 100 years to reach us from that star. Now, one of the major goals of JWST is to discover the first galaxies that formed in our universe, that flickered on in our universe when the universe was only 100 million years old. So when we look at distant galaxies, we are looking backwards in time. We are witnessing the past of our universe. So if we want to see how the first luminous objects in the universe looked like, we have to just see further back in space. So we have the rare advantage in astronomy that if you want to understand the cosmic history, all you have to do is keep looking deeper and deeper into the universe. So what you are seeing here are a collection of images of different galaxies given to us by the Hubble Space Telescope. So in each panel, you can see some number written. So that is the how far away those galaxies are in units of billions of light year. A billion is 1 followed by 90. So from here, the top left corner, you have a galaxy that is 0.5 billion light years, and bottom you have a galaxy that is 13 billion light years. So going from the top left to right and down, we are looking at galaxies that are farther and farther away. And so Hubble has already shown us that how some of these galaxies look in the very distant universe. JWST is going to discover a lot more of these distant galaxies, and it's going to tell us how these galaxies formed in the early epoch in the history of our universe. The other major area where JWST is going to contribute is to understand how stars form. Okay. Now, Dr. Gagan Gupta sir was mentioning about the pillars of creation captured by Hubble. So what you are seeing here is an image captured by the Hubble Space Telescope of a huge gas cloud that is present within our own Milky Way galaxy. So it is in gas clouds like these that new stars and new planets are formed. Our own sun and the planets that are part of the solar system formed from such a gas cloud about 4,500 million years ago. So astronomers are very interested to know how stars form. Now the only problem is these gas clouds are so dense and there is also dust present in these gas clouds that it's very difficult to see what is happening inside these gas clouds. Now, the one way to look inside these gas clouds is to not look at visible wavelength, but at infrared light. So on the right hand side, what you are seeing is the same pillars of creation. It's called the Eagle Nebula, as seen in infrared. And when you look at it in infrared, you see that the entire field is filled with stars. So that is one of the another science goals of JWST. And lastly, what JWST is going to do is it is going to discover many Earth-like planets orbiting around Sun-like stars. So these are called exoplanets or extrasolar planets for short. And the main reason why it's very interesting to discover them is because one of the persistent questions in astronomy is, are we alone in this universe? Could life be present elsewhere in the universe? And so if we want to search for life anywhere else in the universe, the kind of places that we should look for are places that are similar to Earth. So finding planets around other stars, understanding their properties is going to be another goal of JWST. Now, as a telescope, JWST is open for worldwide astronomy community. Anybody from anywhere in the world can apply for time with the JWST, James Webb Space Telescope. Gaining access to JWST is precious. There is stiff competition. So every year, the space agencies would invite scientists, astronomers to submit proposals to use JWSTs to study different objects in the universe, and based on a competitive basis, some of those proposals will be awarded time. Right now, since June of 2022, about 10,000 hours of observing time has been allotted for the first year of operations of the James Webb Space Telescope, that is 2022 to 2023. And this is split into 6,000 hours of observation programs from astronomers all over the world and 4,000 hours of observation programs by people who build the telescope. And if you look at what are the major science areas that JWST is going to do science in the first year, a lot of it is going to deal with the early universe, understanding the large-scale structure of the universe. A lot of science is going to be on understanding how stars form, how planets form around them, etc. So this pie chart shows the different science themes under which JWST is going to carry out its observations. And lastly, just to conclude, I just want to say that JWST it's only 1 year since JWST has been up there in space. But the process of building this telescope, the discussions, the scientific brainstorming, and all the technical things that happen behind the scenes up to the launch of JWST, that goes back all the way to 1989. So nearly 20 to 30 years of brainstorming, hard work of thousands of engineers and scientists has gone behind the construction of this one single telescope. So such ambitious projects do not happen overnight. There's a lot of teamwork and a lot of human resource and collective intelligence that is involved in projects like this. Okay. Now, back in July 2022, the American, European, and the Canadian space agencies released some of the first images taken by JWST. And these are all available online. You can go and look them up. So what you're seeing here are the pillars of creation as seen by the James Webb Space Telescope. Here you are looking at, this is also an image taken by JWST. Here you are looking at several galaxies that are interacting with each other through the influence of gravity. These pictures look very spectacular, and they talk about the remarkable capabilities of the Webb telescope to provide very sharp images. And this is another picture that JWST has recently captured. What you are looking at here is a very, very small patch of the sky. So if you were to take a 1 rupee coin and stretch it at arm's length toward the sky, it will cover a small patch of the sky, which is of the size of maybe a full moon or even less than that. In that small patch of the sky, when JWST observed, it could see thousands of galaxies. So every bright object that you see in this image is a galaxy in itself, like the Milky Way galaxies with billions of stars in it. So the data has started coming in, and there's a lot of discovery opportunities present. Lastly, I just want to mention that if you are interested in learning more about the Webb telescope, you can go to either of these URLs. Most of the pictures and images and animations that you saw throughout this presentation have been sourced out of these two public domains. One is of the American Space Agency and the other is of the European Space Agency. They are available. And lastly, I just want to end this by saying that when the Hubble Space Telescope was launched, people were expecting some discoveries that Hubble would bring forth. Okay. But Hubble outlived its own life, and Hubble far surpassed its own expectations. When Hubble was launched, exoplanets were not discovered, dark energy was not known. The fact that the expansion of our universe, the rate of expansion of our universe is increasing, the accelerated expansion of our universe was not, many things were not known. At the time of the launch of JWST, we know some things about the universe, but there are many things that we do not know. So as one of the pioneers, as one of the key persons who pushed for this entire concept of space telescope, his name is Lyman Spitzer. He was an astrophysicist at Princeton University back in the 1960s, 70s and 80s. So he once wrote in one of his articles that the primary contribution of a space observatory like the JWST is not going to verify the ideas that we already have about our universe, but rather to uncover new phenomena that is not yet imagined. So in other words, what that means is JWST is going to give us what often the public media refers to as frontier science. Science at the very boundaries of our current sphere of understanding. So stay tuned. I'm sure the coming years are going to be very, very exciting as new discoveries come from this remarkable piece of engineering, which is JWST. Thank you. Thank you for listening.
Thank you. Thank you so much, sir, for this marvelous presentation. And I'm sure the students, even if they are science students or they are not, they're definitely going to log into those websites you just mentioned. Thank you so much. And we've got a few questions. So shall we?
Sure, yeah.
So I recently read the news that the JWST, it got damaged. So does it affect its performance? And also, I've heard that unlike Hubble, JWST is not designed for repairing. Is it true?
Yeah, so JWST, as you saw from those animations and pictures, it's a telescope whose mirrors are exposed to space. There's nothing that is protecting those mirrors. So small rocks called micrometeorites, which are present throughout the solar system, they can come and hit the telescope. So when they come and hit, they will come and hit with the force that a bullet would hit. Okay? If you fire a bullet. So these micrometeorites are like bullets that are coming and hitting. So if they come and hit the primary mirror of the telescope, then that can crack the telescope's mirror a little bit. But it's not going to be so serious that the telescope becomes totally dysfunctional. So that's not a major concern. But anyway, it is a concern. The second is a more important question. Since JWST is in the L2 Lagrange point, which is 1.5 million kilometers away from Earth, unlike Hubble Space Telescope, with the current technology, it is not going to be possible to do periodic servicing of JWST. One of the great advantages of Hubble Space Telescope was that it was in low Earth orbit, about 600 kilometers above sea level. So sitting at 600 kilometers above sea level, periodically, once every 5 years or 6 years, on the space shuttle, a crew of astronauts would go up, they would grab the Hubble Space Telescope and they will do all kinds of maintenance and repair, just like we do give our scooters and cars for servicing. So this annual servicing, this periodic servicing extended the lifetime of Hubble Space Telescope. Even now it is working. With JWST, it's not going to be possible with the current technology, but in future, it may be possible to send robotic spacecrafts onto the L2 Lagrange point where they can do some kind of a repair function for JWST, extending its lifetime.
So great, Dr. Anand, बहुत मजा आया, and I see a great teacher today in front of us. Thank you very much. I have very quick questions for you. Can you come back to the slide number 4, sorry.
So
yeah, that's the slide number 4. Yes, yeah, next.
Sure.
Next. Yeah, here it is L3. Is it this L3 is the same as that of the Earth's orbit or something different?
So the L3 Lagrange point is in Earth's orbit itself.
Oh, that's great.
Only thing is, it is on the other side of
on
the
the
sun.
other side of the.
Yeah, so the problem is, if you put something at L3, first of all, it is going to be directly exposed to sunlight, and second is, since the distance is so large, It is the distance between Sun and Earth is 150 million kilometers. So double that would be the distance between L3 and Earth, which means communication. Sending commands to a spacecraft that is at L3 and getting data from it is not going to be very effective.
Yes, that is
so.
understandable.
The accessible points are L1 and L2. All other Lagrange points are a little bit far away, and they are L4, L5, and L3 are all in Earth's orbit.
I'm running out of time at this moment. Dr. Anand, we had many other questions with us, but we will be having another session sometime later for answering all those things, and many exciting session today we had. Thank you very much, Dr. Anand. So, stay with us. Just colleagues and viewers, it's for you now. So next, we are going to come to you on 27th of January with another session, very exciting session on the radiology. The title is the Radiology in the Service of Mankind, when Abhishek Mahajan from the Clutter Bridge Cancer Center, Liverpool, United Kingdom, will be with us in the studios here. So we will be having an exciting session on 27th of January. Please tune in. Thank you.
Thank you. Thank you so much, sir, for this information, and thank you so much, Anand, sir, for being a part of this program. It was a wonderful discussion, and for the new year, for the first session of our webinar series, Listening to Learn, this couldn't have been a better start. And James Webb Space Telescope, out where the stars do not twinkle. This is what we discussed in this particular program. Please watch it if you have not seen it. And for now, we are wrapping up this particular program, but we have a very important announcement for all of you. So, Department of School Education and Literacy, Ministry of Education, Government of India brings you Kala Utsav. It started from 3rd of January, and it is going on right now. It is till 7th of January. So, let's have a glimpse.
India is our land of diverse culture and glory. Let's showcase the art with the glimpses of its story.
We hear the sound of music, we dance to anklet bells. Paint a picture, make some toys rejoice.
Let's do solo acting, let's dance, let's sing and paint.
Some toys rejoice. Kala Utsav, Kala Utsav, Kala Utsav, Kala Utsav.
Children from every nook and corner will perform.
Oh, great!
We will have glimpses from each and every state.
We hear the sound of music, we dance to anklet bells. Paint a picture, make some toys rejoice. We hear the sound of music, we dance to anklet bells. Paint a picture, make some toys rejoice. Kala Utsav, Kala Utsav, Kala Utsav, Kala Utsav.
Kala Utsav, an initiative of the Department of School Education and Literacy, Ministry of Education, Government of India, announces Kala Utsav, organized by NCERT from 3rd to 7th January 2023 at Regional Institute of Education, Bhubaneswar. Kala Utsav.
Kala Utsav.
Kala Utsav 2023 is being organized by Regional Institute of Education, Bhubaneswar, NCERT. So here we are wrapping up this particular program, but we have more programs lined up on eVidya channels. Please keep on watching them. Thank you and take great care of yourself. Namaskar.